Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. Today, I'm going to discuss about the part three of the electromagnetic induction. So, where our basic concept concern is all about mutual induction and inductance. Okay. So, let us understand what is inductance. Now, see here, flux linked, uh, flux linked, closely wound coil are directly proportional to. So, if there is a coil and the current is carrying, so what will happen? If current will increase, so flux will increase, so it means that flux is directly linked with the coil. If the geometry of the coil does not varying with the time, then what will happen? Rate of change of flux is proportional to rate of change of current, right? So we can directly write like this. So d phi by dt, d phi by flux by dt is proportional to di by dt. Okay. For n closely wound coil, if turns are n, so the same magnetic flux link with the all turns. So what will happen? Uh, through the coil change, each turns contributes to the induced EMF. So therefore, flux linked with the coil, flux linkage is equal to n pi. So what you have understood here, uh, earlier if single loop was there, so it was proportional to I, but if n number of loops are there, so n times flux is changing, so it is proportional to the current. Okay. Now the SI unit of the inductance is a Tesla square meter, and we can call this as Henry. 1 Henry is equal to 1 Tesla meter square per ampere. Now, see here, an electric current can be induced in a coil by a flux change produced by another coil nearby flux change produced by the same coil. In both the case, flux is produced is directly proportional to the current. So it may happen that coil there may be a change in a flux due to self current, and there may be a change in a flux due to the outer coil current. Okay. So in both the cases, phi is proportional to the current. So it may happen that due to this coil's current, so there will be change in the flux in this coil, or it may happen due to change in a current in this coil, so there will be change in its own flux. So from the geometry remain constant, then what will happen? We can write like this: d phi b by dt is equal to di by dt. Now, if number of turns are n, so n phi bv is equal to I. So n is equal to phi b into Li, where L is the coefficient of mutual inductance. Sorry, coefficient of the inductance, self inductance. It is your coefficient of self inductance, inductance. Okay. L is constant of proportionality, which is called inductance, and inductance can depend on the geometry of the coil inducing material, depend upon how coil is being placed. Inductance is the scalar quantity, and its unit is Henry. Okay. Now, mutual inductance, the phenomena due to which an EMF is induced in a coil due to varying flux produced by keeping other coil keep nearly is called mutual inductance. So in self inductance, what happens? This is a coil, and when we pass a current in this coil, when we pass a AC source or a voltage source, so what will happen? It will create a change in the flux in its own coil. Okay, so this is known as self inductance. But when we talk about the inductance produced due to different coils, so if this is your coil like this, okay, if this is your coil like this, and if this is your power source, and there is another coil like this, got it? So it is creating a inductance from outside, so what will happen? It will change the flux. So this is known as mutual induction. Now see here, consider two long coaxial solenoid, each of length L. So it may happen that you can consider a coaxial means same axis coil. I'm just drawing it, so you can see from here coaxial means same axis coil. So two coils are there, in one having a radius R1 and another having a radius R2. Okay, let radius of the inner solenoid S1 be R1 and the number of turns per unit length N1. And for outer solenoid S2, their radius is R2 and number of turns is R2. So the total number of turns is be N1 and N2 on both the coil, S1 and S2. When the current I2 is set up in S2 coil, so if you observe here, so outermost coil I have just or we have just put a current I, that is I2. So what will happen? So when I2 is set up, then it links a magnetic flux through S1. Let flux through S1 be phi 1. So it has when you pass a current, so what will happen? It will link a magnetic flux to the inside coil, right? So from here we can say that N1 phi 1 is proportional to I1, and N1 phi 1 is equal to M12 into I1, where what is M12? M12 is the mutual inductance or a coefficient of mutual inductance of S1 with respect to S2, of S1 with respect to S2, and it can be found with the help of geometry, certain geometry. Okay. Now from here we can also find N1 pi 1. So this is equal to N1 into L into pi R1 square into mu naught N2 into I2. So finally we will get as N1 pi 1 is equal to mu naught N1 N2 pi R1 square into L into I2. Okay. So this is equation number 2. So from here we can also find that M12 into I2. If we M1 and 1 2 into I2 is equal to mu naught N1 N2 pi R1 square into L1 I2. Now if you want to find M12, so M12 will be M mu naught N1 N2 into pi R1 square L. Now we now consider a reverse case. When current I1 is flown through the S1, then the flux will be N2 phi 2 is equal to M21 into I1. Okay. Now just we put here everything, we will put as it was. So when we put here, so we will get as mu naught N1 I2 into pi R1 whole square. From 3 and 4, what we observe that we are getting M21 into I1 is equal to mu naught N1 N2 by pi R1 L1 square. Therefore we see that mutual inductance M12 or M21 both are same. So the value of mutual inductance are always same. So from here we can find that M21 is equal to mu1, number of turns in one coil, number of turns in two coil, and into pi into R1. R1 is the radius of the smaller coil, a smaller radius coil having a smaller radius, we can use that, and L is the length of the coil. Okay. So if there was a medium relative permittivity, then just you can add on mu. See here, if there is a relative permeability, just you write mu naught into mu r into n1 into n2 pi r1 square into L. Okay. The mutual inductance of the pair of a solenoid also depends upon the separation and the relative orientation. Okay. So from here we can also get this n1 pi 1 is equal to mi2. So finally we differentiate it. So we will get as EMF, because this is the definition of EMF only. So EMF is equal to minus EMF of the coil produced is equal to EMF E1 in the coil 1 is equal to minus mutual inductance into D I current in current passed in a coil 2 divided by dt. So this is very important formula. Okay. So now previous year question, just we can see here. A pair of adjacent coil have a mutual inductance of 1.5 Henry and the current in one coil changes 0 to 20, that is delta phi. D phi is equal to 20 ampere. 20 minus 0, that is equal to 20 ampere, right? And what is the change in a flux linkage in the other coils? So d phi by dt is equal to mutual inductance by del I by dt. So from here dt cancel. So change in a phi is equal to m by 2. So change in phi is equal to 0.5 into 20. So from here we can tell that wave change in a flux is equal to pi Weber. Okay. And this is your change in a current. Got it? Next, self-inductance. The phenomena due to which an EMF induced in a coil due to varying current through the same coil is called induction, and varying current through the same coil. When the coil is same, not coil is same, And in this current, if I am giving a current and there is a back EMF is being produced by this coil due to change in a flux, then phi can be written as phi proportional to I, and phi is equal to Li, where L is the proportionality constant known as self-inductance or coefficient of self-inductance. So inductance of a solenoid, consider a solenoid of a number of turns n per unit length of a radius I. So we know that n phi is proportional to I. So n phi is equal to Li. We can write like this. Now we can observe from here self-inductance. So let us one we can write here n phi is equal to Li. So put here n phi is equal to Li. So L can also be written like this, NL into mu naught Ni into pi a. Phi is equal to mu naught Nia. So this is an area. So from here n phi is equal to mu naught n square pi square L into I. So from 1 and 2 we can write here Li is equal to this. So finally mutual inductance L is equal to mu naught n square pi a square into L. So we can write this, right? Now for a solenoid with the core relative permeability mu r, just add on mu r. So finally we have got the value of mutual inductance. It is a self inductance. Now if current through the coil is varied with the time and EMF is induced, so n phi is equal to Li, and d phi by dt is equal to L di by dt. So from here EMF is equal to minus d phi by dt. So from here, EMF is equal to minus L di by dt. We can write like this. So I hope you have understood this. Now note, self-induced EMF is also called back EMF, and it opposes any change in current in a circuit. Physically, self-inductance plays the roles of inertia. Okay, so the electromagnetic analogous of a mass of a mechanics. Now see here, one more question is that a plot magnetic flux versus a current is shown in a figure of a two inductor A and B. Which of the two has the larger self-inductance? So this is flux and this is your current. So we know that phi is equal to Li, or from here phi by I is equal to L. So phi versus I is equal to L. That the slope of this will always give you L. So the more slope means more L. So A has more slope, so A has a larger self-inductance. So therefore the greater slope, greater is the self-inductance. That is, A has a greater self-inductance than a B. So I hope you have understood this. So I hope you have understood this. So in this way we can end this chapter. Thank you for watching my video.